Hi, welcome to this video on our paper Optimistic Data Parallelism for FPGA Accelerated Sketching. I'm Martin, I'm a software engineer at Kibo, but this paper was actually written during my time at TU Berlin's Database Systems and Information Management group, and I did that together with the other wonderful people mentioned on this slide. And with that, let's get right into it and start with a bit of background. First, some background on sketching. Sketches are a useful class of summaries that can be constructed over data at rest or streaming data, and sketching is the process of creating these summaries. After creating a sketch, you can query the sketch for interesting attributes of the data it has been constructed on. So for example, you can query it for the number of distinct values or value frequencies. And this is obviously very useful for many tasks, including approximate query processing, but also, for example, heavy hitter detection. Sketches have a lot of useful properties, and in particular, they can be constructed in small space, and they can also be queried with low latency. However, the computational burden shifts now from querying the data to actually constructing the sketch. And thus, we want to construct those sketches at high throughput. Field programmable gate arrays, or short FPGAs, have been found to be a good architecture to perform sketching at high throughput. In particular, there have been publications that even propose FPGA-based data analytics accelerators based on sketching. And a couple of them are listed on the slide. And especially in these setups, high throughput is as crucial as ever. If you don't know what FPGAs are, I got you covered on this slide. So essentially, it's a chip that provides you with reconfigurable logic resources, and those allow you to create custom hardware based on software. And besides those logical resources, FPGAs also come with a couple of auxiliary resources. And in particular, they provide us with high density memory in the form of so-called block RAM elements, or short BRAM. And here on the right, you see a high-level illustration of an FPGA. And here in white, you see logic resources. In blue, you see those high-density memory BRAM elements. And then we have digital signal processing units. But for this talk, you're good with logic resources and block RAM elements. The important thing is these resources are limited, and the more complex your logic gets, the more of them you consume, up to the point where your logic can't get any complexer because you've consumed all those resources. Furthermore, it's important to note that this reconfigurability of FPGAs comes at a price. So custom circuits on FPGAs run at a much lower clock frequency, so typically a few hundred of megahertz. That is much lower than, for example, the few gigahertz your regular old GPU or CPU provide to you. And to compete in terms of throughput, FPGA designs have to exploit parallelism to make up for that. And this parallelism can either be data, task, or pipeline parallelism. And usually it's a combination of all of them. As a last piece of background, let's talk about sketches. The term is used in various connotations, so it's essential to state a definition. This paper considers every summary a sketch that can be constructed based on the select update model. And that model, the sketch, is a matrix. And for every input value, we first evaluate a select function, and it selects one of the entries in each row. And then we evaluate an update function, and that function determines the next state of each entry. And it does that based on the input value and based on the previous state. The select function is commonly given by a family of hash functions, and the update function can involve hashing as well. And that's why both functions also have this additional argument theta here. And that is just an optional random seed. The select update model generalizes quite a few popular sketching algorithms, and that includes count-min, hyperlog-log, or fuzz-HMS. So whenever we're talking about sketches in this talk and in this paper, we're talking about algorithms that can be described in terms of a select and an update function. Now that we've established the background on FPGA accelerated sketching and its individual components, let's talk about the subject of the paper, optimistic data parallelism for FPGA accelerated sketching. On a high level, the state-of-the-art architecture for FPGA accelerated sketching looks as follows. For each row, we have a compute unit that is responsible for evaluating the select and update function, and we have state memory that is responsible for storing and providing the state of the individual entries in the row. This architecture is set up such that the compute unit is consuming one input value in each clock cycle, and the state memory is also able to consume one read and one write request per clock cycle. Thus, the overall architecture has a guaranteed throughput of one input value per clock cycle. We also call that processing at line rate, which means that we can process data as fast as it arrives at the device. In particular, this also means that throughput is entirely independent of the data distribution, which is quite a handy property to have. As I mentioned earlier, one input value per clock cycle is not a very high throughput to have, given that FPGAs operate only at a clock frequency of a couple hundred of megahertz. So if we really want to get throughput that goes beyond 100 gigabits per second, we actually have to exploit data parallelism to make things faster. And the way this can be done is essentially by just replicating these circuits. That means we process the input values simultaneously instead of only one, and then we essentially just replicate the architecture. Thus, we have an entire replica of the sketching hardware for each of the input values. And since sketches are mergeable, we can then later combine these individual sketches into a single one. This architecture has two advantages. First, we keep the guaranteed throughput from before, and two, this is very easy to implement. So you just instantiate a couple of replicas of the hardware and you're done. Why would we call a beautiful and simple architecture like that pessimistic? Well, by replicating the entire architecture for each input value, we are leaving hardware resources underutilized, especially in terms of the state memory. To see that, we have to zoom in on the state memory. On this slide, we see how the state memory is implemented. If you remember from earlier, FPGAs provide memory in the form of independent BRAM elements. The pipeline memory architecture just daisy chains them, and each BRAM element is responsible for a range of the state entries in the row. This architecture guarantees processing one read and write request per clock cycle, but each request is only handled by one single memory segment and its corresponding BRAM element. The other memory segments will just forward the request. And this is what's pessimistic about the architecture. We're using a memory architecture that underutilizes the available memory elements, while at the same time, as shown on the slide before, replicating state memory together with compute units for each input value. However, the state memory and the auxiliary logic around it are usually the bottleneck in terms of resource consumption on the FPGA. And this is the motivation for proposing an optimistic architecture for FPGA accelerated data parallel sketching. We were asking ourselves, can we do better? To reduce resource consumption, we would much rather have one single compute unit that consumes all of the D input values together and have one single state memory that's shared among all these input values. And as we introduce a shared resource now, there can be resource conflicts that require resolving. Thus, we need a mechanism that tells the outside world to stop sending us new data until these conflicts are resolved. This is called stalling the architecture, and we have added this ready signal here, and it essentially tells the outside world, okay, we are ready to process data, or please stop for a while because we are stalled. Of course, this wouldn't work with the state memory that I showed you earlier, because this state memory can only process one single read and write request per clock cycle, and an architecture that would use a state memory like that would just be hopelessly overloaded by the requests coming in from multiple simultaneous input values, and thus the architecture would be stalled all the time. So we have to come up with something smarter for the state memory. To solve the issue, we are not using a single state memory, but rather several instances of state memory that operate independently, so-called banks. Each bank handles a different range of offsets, and now the architecture can actually process several memory requests in parallel, given that they are not trying to access the same bank. In this case, we have twice as many banks as input values, which the paper shows to be practically the best setup. To solve this, we extend the compute unit by dispatch logic that assigns each request to the corresponding bank. And furthermore, we add queuing after dispatching to avoid us from having to stall right away every time more than one request is issued to the same bank. And now the architecture is truly optimistic because it's not replicating memory anymore, while at the same time allowing for conflicts and hoping they aren't happening too often. However, if we have a skewed input data distribution, we can still end up in a situation where the architecture is stalled because almost all of the requests will hit the same bank. And as real-world data tends to be skewed, we propose an additional solution to deal with skew and heavy hitters. This additional solution requires us to slightly modify the select update model by splitting an update into a map function that computes an increment and a reduce function that combines these increments with the previous state of the entry in the sketch matrix. This reduce function has to be associative commutative, and there has to be an identity element. Now, in practice, this is not really a restriction because the presence of such a map and reduce function follows from sketches being mergeable. The reduce function is the key to our merging techniques. We can not only merge increments with previous data entries, but we can also merge increments with increments. You see an example for the count min sketch here. We have offsets coming from the select function, which is just a hash function, and increments coming from the map function, and those are just plus ones. And now we can merge the increments with the same offsets. And we can do that in a merge tree and just use the neutral element for all increments that don't share the offset. And in this case, we can actually apply a single update to the sketch matrix instead of applying 3 of them. Thus, this technique allows us to take pressure off the individual banks in case of skew by reducing the number of requests the banks have to handle. Finally, let me show you the optimistic compute unit in a bit more detail. Now here we have an example with 2 input values. And first we evaluate the map and the select function, and then we pass the offset increment pairs computed to the horizontal merger. And horizontal merger is just buffering the offset increment pairs and merges increments with the same offset and passes them further down the architecture. Then the dispatcher takes over and assigns the offset increment pairs to their corresponding bank, and then it puts them in a queue. And then we have a vertical merger for each of the banks, and the vertical merger just checks the queue heads and also tries to merge increments with the same offset when popping elements from the queues. And then finally, the requests containing the offset and the increment are then forwarded to the bank. Now, let me highlight a couple of findings from our evaluation. First, let's talk about stall rates. That's the share of clock cycles the architecture is not doing useful work because it's resolving conflicts. We have computed that value here with a simulator, and bank memory alone is really good with uniform data. So what I show you here are the results for Zipf distribution. That means that the data is skewed. Now, we ran our experiments for different number of input values. And on the y-axis here, you see the stall rate. And on the x-axis, we gradually increase the amount of resources we invest into merging. So in the beginning here, you see that we have no mergers at all. And there, the architecture is barely doing useful work. So we are stalled like a significant share of clock cycles. Then if we add a vertical merger, this already drops significantly. And then if we gradually increase the buffer for the vertical mergers, we can even get rid of the stalls altogether, which is quite a good result. And in the paper, we tested real-world data sets as well, and they essentially allow for the same conclusion. So if we invest enough resources into merging, we're actually able to prevent stalls almost entirely. Now that we've convinced ourselves that optimistic data parallelism with banking and merging works well in terms of simulated stall rates, let's check if the architecture works as good in an actual application. We use an approximate reprocessing application based on variations of the count min sketch, and it tracks count, sum, min, and max over input data sets consisting of key value pairs. We implemented this on a Xilinx U250 data center accelerator. And now that we've seen that an optimistic architecture serves us well in terms of sketch size and accuracy, let's look at the throughput of our implementation compared to an implementation on a high-end GPU and CPU over various data sets. We see that we are able to outperform the CPU and GPU baseline by roughly 2x. We're actually able to make up for the smaller clock rate of the FPGA by aggressively exploiting parallelism. Furthermore, we see that our implementation has a very robust throughput of 575 gigabits per second over the shown datasets. The reason for that is that the architecture never stalls, so here the throughput of the pessimistic and optimistic architecture are the same. We are reading data from the RAM on the device, and it does not provide new data in a few percent of the clock cycles, and that's more than enough for our optimistic architecture to transparently resolve conflicts. In this video, I showed you that optimistic data parallelism allows us to get the same throughput with fewer FPGA resources. Optimistic architectures share the state memory among the parallel input values, and they use a banked memory architecture to handle the simultaneous request to memory and employ merging to reduce congestion. What this architecture can't give you is a hard guarantee on the throughput, because there can be stalls. But in practice, we have shown that stalls can be avoided entirely. Thank you for watching this video. Feel free to read the paper, which, of course, goes into much more detail on the approach. If you're interested, feel free to check us out on GitHub, where you'll find the code for this paper and the Scotch code generator that our implementation is built on. Bye.